Hello, and welcome to Chem Talk. Today, we'll be learning about chirality, an important organic chemistry subject which describes the orientation of molecules in 3D space. Chirality has countless applications throughout medicine and biological chemistry, because molecules with different chirality interact with other molecules in different ways. For example, almost every amino acid is chiral, and this chirality is in part responsible for the formation of secondary structures in proteins. So, let's talk about it. A chiral molecule is a three-dimensional molecule that is non-superimposable on its mirror image. This means that if you have a molecule and its mirror image, there is no possible way to orient one molecule such that it is the same entirely as the other one, and all parts of the molecule overlap. A common example for this is human hands. If you take a look at your hands, they are mirror images of each other. But if you try to lay your left hand on top of your right, for example, you'll see that only the middle fingers overlap. Your left pointer finger matches your right index finger, and your right index finger matches your left pointer. Thumbs are paired with pinkies, rather than thumbs with thumbs and pinkies with pinkies. So, they're non-superimposable mirror images of each other. This concept is similar in molecules. For instance, if you look at a molecule like CH3Cl and draw out its mirror image, like so, it's possible to orient this mirror image such that it overlaps perfectly with our original molecule. If we just rotate this molecule around, we can place the molecules on top of each other such that each hydrogen matches a hydrogen and the chlorine matches the chlorine. So, this molecule is superimposable upon its mirror image, meaning it is not chiral or achiral. If we look at a molecule like CH2ClBr and draw its mirror image, it's still possible to orient this mirror image such that each molecule corresponds with itself. This is pretty hard to visualize, so I recommend either using an online 3D molecule builder or getting a molecular modeling kit. If we rotate the molecule, we can do so such that bromine matches bromine, chlorine matches chlorine, and each hydrogen matches a hydrogen. This molecule, too, is superimposable upon its mirror image, meaning it is also achiral. We finally get a different result when we have 4 different substituent groups. If we have a molecule like this, and we draw its mirror image, there is no possible way to orient this molecule's mirror image such that it overlaps with the original molecule. This molecule is non-superimposable upon its mirror image, meaning it is chiral. In this molecule, our chiral molecule from the last slide, carbon is what we call a chiral center. A chiral center is an atom, often a carbon, that is sp3 hybridized, meaning it has 4 sigma bonds, and has 4 entirely different substituent groups. So, when we're identifying chiral centers, it's best to look for a carbon with at least 3 sigma bonds, and the 4th one can come from an implied hydrogen. If a molecule doesn't have any chiral centers, it is almost always achiral. It is possible for a molecule with chiral centers to be achiral too, but we'll cover that in a separate video about stereoisomers. In this molecule, the carbon in the center is bonded to 4 different substituent groups, making it a chiral center. Let's take a look at an example. Label each molecule as chiral or achiral and identify all chiral centers. Molecule 1, we can immediately tell, is achiral because it's 2-dimensional. In order for something to have chirality, it has to be a 3-dimensional molecule. Okay, for number 2, let's first look for chiral centers. This spot looks like it could be bonded to 4 different groups, but let's take a look. We have a bromine, an implied hydrogen, and a ring. If we go around the ring this way, we have 1, 2, 3, 4, 5 carbons before we get back to our center. And if we go the other way, we also have 5 carbons. So, these groups are technically the same. And to have a chiral center, we need 4 different substituent groups attached. So, this is not a chiral center, and this molecule, then, is achiral. Let's take a look at number 3. We have the same thing, but with an added methyl group. Here, we have 2 prospective chiral centers, here and here. Let's start with this top one. Its substituent groups are a methyl, an implied hydrogen, and a ring. If we go around the ring this way, we'll have 1, 2, 3, 4 carbons and a bromine substituent. If we go the other way, we only have 2 carbons and then a bromine substituent. So, this center is technically bonded to 4 different substituent groups, making it a chiral center. Let's take a look at our other potential chiral center. We have a bromine, an implied hydrogen, 2 carbons, then a methyl, and 4 carbons and then a methyl. So, 4 different substituents. That is a chiral center, and this is a chiral molecule. Let's look at number 4. Here, we have 2 prospective chiral centers again. Let's start with our leftmost one. It's bonded to an ethyl group, a propyl group, this group off to the side, and an implied hydrogen. That's 4 separate substituent groups and 4 different substituent groups. So, this is a chiral center. Our second prospective spot is bonded to this piece here, an implied hydrogen, a methyl, and a methyl. That's only 3 different substituents because there are 2 methyls. So, that is not a chiral center. We do have 1 chiral center though, so it is a chiral molecule. What does chirality have to do with biology and biological systems? Chirality can be seen in lots of places throughout biology and medicine, but today we'll look at its impact on amino acid formations. The chirality of amino acids plays a big part in the formation of secondary structures of proteins, such as alpha helices and beta pleated sheets. If even a single amino acid is in the incorrect chiral configuration in one of these structures, the entire structure falls apart and will not hold. Chirality plays a key role in every protein in our body, as almost every amino acid is a chiral molecule. In summary, we learned that a chiral molecule is a 3D molecule that is non-superimposable on its mirror image. We learned that a chiral center is an atom that's sp3 hybridized and has 4 sigma bonds to 4 entirely different substituent groups. And we learned that chirality has a big role in biological systems, such as within amino acids and the formation of proteins. Thank you for watching, and be sure to check out our website, chemistrytalk.org, for more great chemistry, biochemistry, and organic chemistry tutorials and content. If any of the terms in this video are new to you, check out our other videos on stereochemistry and organic chemistry.